Okay, guys, we have attendance 1201. Also, we have a discussion. I defined something that you guys discuss about designing the processor. I want you to think about it. I'm going to give you some samples today, but based on what you are working on or the project that you want to do or whatever come to your mind, we can design a processor, not a general purpose processor, very specific processor for your task with limited number of instructions. It's just design. I want you to think about it, write your idea, and talk to your friends. And yeah, it's kind of discussion group. I hope be useful. Okay, so don't forget to do attendance. Let's get started. So what we want to do this week, we are try to talk about pipelining. One method of parallelism, do parallel things at the same time. In processor is pipelining. Is the method to increase clock per instruction. We can see how. Last class, we talked about processor design, specifically control design, data path design. We're going to talk more about control today a little bit before go to pipeline. But in pipelining, we're going to see how we can actually split one big instructions to pieces, that those pieces can be done in a shorter time. And this going to give actually parallelism and increase clock per instruction. I mean, reducing clock per instruction. It means increasing the performance. How we can design pipeline, we're going to see with using some registers, pipeline registers. We can divide a big actually data path to multiple pieces. This is not for today. Maybe for next class, we talk about this part, how we can design a pipeline processor, multi-cycle processor. But today, we're going to just introduce how pipelining works. Regarding control last class, we didn't finish all of it. I'm just going to cover this. We mentioned that we have normally, at least for RISC-V, we have two controllers. One controller is a main controller that get opcode, 7 bits opcode, and make control signals. And because some instructions, in addition to opcode, need actually those function bits, function 3 and function 7, we give those values to another controller just for ALU operations. So we get those parts from instruction register. In some processors, like in a one-cycle processor, even we don't have that instruction register. We just can take that from the bus. When the bus coming out from this instruction memory, we can take those bits off. And we can take those and give it to this ILU controller to make signals for ILU. So we have two controllers in this computer. In some computer, you don't need to have two. Just one is enough. But here we have two. One is a main controller to make all these signals. As you can see, this is the main controller. Make branch signal, memory read, memory write, memory to register for this multiplexer. ILU operation. This ILU operation, it's multiple bits that specify the category of the instruction, like R type, I type, whatever. And then which instruction inside, for example, R type is specified using function 3 or function 7 coming from instruction. So that's why we have two ILUs, two controller, one for ILU, one for the main controller. So we already explained last class, but we passed it very fast. I wanted to emphasize in this. So as you can see, the data paths coming from program counter, instruction memory, register files, even this multiplexer is part of data paths for some instructions, at least for R-type instruction, we need to consider the delay here as well. ILU, for R-type, we don't need to go for memory. We can use this line and come back and write it back here. So is a start from here, program counter, instruction memory, registers, multiplexer, ILU, another multiplexer, and write back, register again, register file again. Okay? So that's a data path. Any question about this? Anything that you don't know about that? Like, you need to know all these parts. What is this add doing? What is that one? What is this shift doing? Multiplexers, ILU control, immediate generator. This is immediate generator. Make the 32 immediate value to 64. We can use it using ILU. You need to know all those parts. Here we already covered about R-type, but I want to emphasize in this R-type design that some part of this architecture, some part of this data path is gray. The parts that are gray, it means is not yet used by using R-type. So R-type doesn't use this immediate, but doesn't mean that this is disconnected. This is still connected. This is still working, but we are not using the value that is generating. That the value that is created here, 64 bits, is still going to get created, but we not use that. It's just wasting. What about we design the hardware that, for example, when some parts is not used, we use it for another instruction. That's the idea of pipelining. We're going to see that soon. But to do that, we need to divide this big data path to multiple smaller data paths. How we can do that, we're going to see we can use the registers between. We call them pipeline registers, big registers, like a very long register we put here, here, here and divide it to multiple, you know, slices, and each slice can do in a different cycles, the smaller cycles, and but it has some issues that happen that we can talk about. That we call them hazards. Sometimes instructions are related to each other. Sometimes instruction need one, for example, resources. Both of them need one resources, and we just have one, for example, register file, and two instructions need a register file. How we can use that? Or sometimes we have control functions, and control functions destroy all of the pipeline. You know, we can see that. So this is for R-type data path for one cycle. This is one cycle because we don't have any register in this between. You know, we already explained how controller can create these control signals. This is the part that you can use, for example, Verilog to design the controller. This is for load. As you can see, load is, we can say load is the longest data path and is the slowest instructions in most of computers. Why? Because you start from program counter to fetch instruction from instruction memory, decode it, access to registers from register file, multiplexer, ILU, data memory, and write the result back in register file again. You know, this is start from here and come back and again here. So if I want to show that data path is something like that, we are coming from here and write it back here. This is the path that data go in one cycle. We do this stuff in one cycle. But this cycle is supposed to be big cycle. So we last class we already explained how the controller gonna create these control signals for load operation. Also, last class we explained about branch, and we mentioned that branch equal is, so as you can see in branch, you start from program counter, fetch instruction, take some registers because you are comparing two registers, and if they are equal, so you are doing this ILU to create the output, and then the output gonna go here and write back inside this program content. This is the path that data going, you know. Even this part coming from immediate, we also need ILU. Why we want ILU? To compare those two registers to see if they are equal. We can do jump. If not, we don't do jump. And how we can select we are doing jump or not with using this multiplexer. And with one AND, we are checking if the 0 is 1, it means they are equal. And if it's not, we're going to go to the next instruction that coming from this program counter +4. So this is what we already talked. Let's go for this. I want you to think about this. Let I define this. I want you to solve it. Use iClicker. Let's see, where is my iClicker? Start the class. You need to enter this one. Okay, so let's pull. Short answer, start. I'm going to explain it a little bit. So what's happening here? We have a RISC-V structure processor with following information. we give some data. We say, okay, latencies. Latencies means the time to pass, for example, from start to go to memory to finish, go out. So memory, instruction memory and data memory is spent 250 picosecond. So picosecond means 10 power minus 12 seconds. And register file, this has lots of details in this table. I gotta explain. Register file need this much time to pass register file. Multiplexer, even we have multiplexer, ILU, adder, need this much latency. Latency, as I mentioned, the time start to end. And a single gate, even single gate given, but we're not gonna use it in this example, but maybe in another example use it. Register read and register setup. Register setup means register write. This register read is for program counter, because the only, in this design, the only register that we are working directly is a program counter. But for writing, this register setup is for writing in register file as well. Register file, reading and writing has different time in this design. In some design, they are equal, but in this design, they are different. We gave different time. This is for writing to register file, and this is for reading from register file. Why? Because reading from register file has so many things. At the same time, can read two, and also doing decoding as well. Anyway, sign extension need this much, and the control signal need this much too. So we are asking, what is the, okay, assume we are doing add, so R type instruction. So if we do R type instruction, first of all, we are asking what is the total latency. What is latency? I explain here. Latency is a overall time from start to finish the result. The total time it takes for a single instruction to get executed from start to finish. So we need to consider all the data paths that we need for this add, that is R type. So we need to remember which one of those involve, and we need to add them together. But to make it more simpler, I already mentioned the data flow is like that. We start from program counter, instruction memory, register file, ILU, multiplexer, even multiplexer here constant because it's given. And a register and register setup means register write. So, okay, so try to do it. Let's see. You just need to see some, okay, first of all, PC didn't mention. So we didn't mention, but here you don't see PC. PC is exactly equal to a register read, because PC is a register. Okay, so we want to read it. You read the program counter. Instruction memory is given. Instruction memory here. As you can see, instruction memory and data memory has the same latency. That makes sense. It's memory. And the register file, this is reading register file. So reading register file is given here, register file. ILU is always given. Multiplexer is given too. Yeah, here is 25. And register setup is a write back. Register setup is not equal to actually register file in this example. In some example, we just consider them same. But here we gave lots of details. And register setup is actually write back in register file, but it has different timing. 20. Okay, so if we add them together, so let's see how many people. Yeah, mostly correct, but try to do all. Try to add them. Program counter is 30. I don't know what I can type here. Instruction memory 250. This is in front of it. I can't. Oh, okay. Move it. I don't know what happened. Anyway, I can see that because it's in front. Oh, okay. I moved that. Register file 150. 150 ILU 200 multiplexer 25 register 20. So in overall gonna be 675. So I think many of you did correct. Let's see. Yeah, we have some wrong, but mostly correct. Okay, any question about this? Maybe you ask me why you didn't consider control. Control can be done parallel. In the data path, we don't consider control in a data path. Control can be done parallel. Okay, so this is, so it was a couple of things in this example. First of all, PC is at same time as reading registers. This is one. The register file and writing register setup are sometimes different, sometimes equal. The control, we don't consider it in this data path. Control is not considered in the data path. Or we can say control is most of the time, in this example that we are in one cycle, because this cycle is big enough. Yeah, if the controller spend more time as one cycle, we need to always consider that. But as you can see, the control is very little. And the clock cycle for here is 675. So this means that this instruction to can execute that, we need this much time, this much picosecond time. And the clock cycle need to be bigger than that. Okay, and as you can see, that's a big enough that 50 can be done parallel. But if this is bigger than that, we need to make a clock cycle same as the control, because the control is a bigger than that. Okay, so don't need to mix up everything. Okay, any question about this? This is the kind of samples that we're gonna see in your quizzes and probably your assignment and stuff, something similar to that. We can play with that in a different way, you know. Just wanted to make you. Okay, let's go to pipelining. Okay, right now we have enough idea what's going on. When we have a big clock cycle and everything needs to be done between, sometimes this clock cycle is big. And as we already talked, performance is inverse of CPU time, and CPU time related to clock per instruction, clock cycle time, and instruction count, the number of instruction. So clock cycle is something that needed like a technology. We are not easily can play with this clock cycle. We are not able to play with that. It needs, lots of issues coming up when you actually decrease this clock cycle time. You are dealing with so many technological issues and make the processor, hot, and you have problem. But instruction count is also, this is based on the benchmark, and you're not, but this is something that we can play with that. Clock per instruction. Can we decrease clock per instruction instead of, for example, using, for example, 2 clock, bring it down to whatever less or whatever, to bring this CPU time less. If the CPU time become less, the performance going higher because performance is 1 over CPU time. So we already explained about this. The one way to can actually change this clock per instruction is pipelining. Let's see what pipelining means. In this example, you can see what's going on. This is the example of actually laundry. When you want to do laundry, imagine you have multiple laundry. So that's one case. To be successful in pipelining, you need to have multiple tasks, not just one task. You need to have many tasks. If you have just one laundry, it doesn't make sense to make pipelining. But if you have, for example, 4 load of, you have lots of clothes to do laundry and need, 4 load, for example, loads, you can do, if you do normal, imagine you divide that to actually wash. You can divide to dry, fold, and I don't know what we can do, put away, or maybe closet, put it in a closet. So imagine washing takes 1 hour, drying also takes 1 hour, fold takes half an hour, and putting in a closet, imagine need half an hour as well. Okay, that's just example. So one time, 1 load of laundry need 3 hours in this example. If you have 4 load, it's going to be 12 hours, long time. So in overall, 12 hours, you need 12 hours in overall, okay, to finish these 4 laundry. Okay, let's do one trick. Instead of, first you need to consider some assumptions. First of all, you need to consider that, for example, washing and drying can be done together at the same time. Or folding, washing, and drying can be done at the same time. Or, for example, put them back in a closet, and folding still can be done in the same time. This is the assumption that we need to have. We're going to have the same assumption with computer as well. So if you have these assumptions of what we need to do, first of all, we need to see which of these subtasks actually has a maximum time. So the maximum time of these 4 subtasks is washing and drying equally, so 1 hour. So we consider that as a clock. Consider that as a clock. So this is how we consider. So we divide this big task to multiple subtasks and find the maximum. So the maximum timing, maximum delay is 1 hour. Even though, for example, folding need half an hour, we need to consider 1 hour. Why? Because in here, folding and washing need to do at the same time. So we need to wait. Even though we are finishing folding earlier, still we need to wait. So this is happening in pipelining as well. So as you can see here, even though, for example, this closet needs half an hour, we need 1 hour for each of these subtasks. So 7 hours overall for 4 instructions. And what is a speed up is 12 over 7. That's a speed up. We want to see how much we are faster. We get this much faster. So this is an example of pipelining. We do the same idea in computer. Instead of having one instruction, one load of laundry that takes 3 hours, we can break that down to subtasks, to sub parts, and do those parts faster. But we need to consider which one is the slowest one and get the clock based on that. So clock here is like this. Oh, no. Like we do here. But clock here is like this. Then write it. Because this is a smaller task, we can do it faster. That's the reason. Okay, any question about this example to go in real processor? So the idea is here, a split instruction into stages. Instead of having one big, we can break that down, split that to the small stages. And but we need to have multiple instruction. We need to have multiple loads. If you have one, not make sense. So we need to process several instructions at the same time simultaneously. And each instruction move one stage forward every clock cycle. So, and we had that before in at least RISC-V, we already divided finishing one instruction to stages. Remember, instruction fetch, decode, execution, and memory and write back. Instead of having this washing, drying, folding, and closet, we can do instruction fetch, instruction decode, and write back. Same way. That's called pipelining. So probably you have lots of questions. You say, oh, maybe because, for example, one issue that we have here, maybe instruction fetch and memory, they have different, like a previous example, this need, for example, 100 picosecond, memory need 250 picosecond. They are not equal. So if we consider the maximum timing, so we kind of make it slower in one instruction. That's true. We make it slower with one instruction, but with multiple instruction in overall, it gets faster. Any question? You have question, Josh? Okay. Any question about this part? So the pipelining happening in so many manufacturing, you are doing that too. Instead of, for example, to make one part, they can divide that big part to small, sections to make that part, and different people doing little pieces. And maybe first product can create it after 10 steps, but after that, every product just need one step to go out because it's already past 9 steps with different people. This is happening in manufacturing a lot. This is called pipelining. We can use it in computer as well. Let's go a little more deeper. So the things that we need to consider, the idea that we need to consider is that we need to start instructions before finishing the first instruction. For example, here we have load, word, store, and add. So when we fetch, load. When we want to decode it, the fetcher is empty. The part related to the fetch is empty, so we can fetch another instruction. When this gets executed, ILU is busy. The decoder is free, so we can decode this and fetch another one. As far as we are not interfering each other, as far as we are can be done, there is always the wave. Two of these also using same thing, we can fix that as well. That's, we call them hazard. That we're going to talk about that next class, how we can fix them and go through. Like for example, some instruction like a store doesn't need write back, or add doesn't need memory. So that's okay. We just give a stall. We just give an empty space for that. That's fine. Yeah, we are sacrificing some extra time, but in overall, the performance, the throughput going very higher if we have multiple instructions. So the overall execution time is something that we need to consider. Oh, okay. And it's improved like utility for the hardware. So another thing that we need to consider is a clock, this formula that I mentioned. The performance actually coming from CPU time, inverse of CPU time. And in this structure of pipeline, we are not changing clock cycle. We are not changing instruction. We are changing clock per instruction. We are actually fixing that pipeline, mainly reduce clock per instruction. And a speed up in an ideal way, in a maximum way, is a number of pipeline stage, but most of the time is less, as like that example that I mentioned for laundry. Even though you divide it to 4, but the speed up was almost 2, because 2 of operations, like folding and putting in a closet, they just want half an hour, but we spend 1 hour for them. Here we're going to have the same issues as well. That's why this is not exactly 5 times. It's always less than 5 times. That's the ideal case, that be 5. Is pipelining the only way? No, we have other methods as well. Like another method is superscalar. In superscalar, you are using like completely parallel to instruction. 2 instruction fetch, 2 instruction decode, 2 execution, memory, and write back. That's called superscalar. Superscalar is another method of parallelism, but we can talk about that later. It just need to double or triple resources. Okay, that's like some extra information about pipelining. Let's see some example for actually load. Because load instruction is longest instruction in most of computers. Why is long? What is slow? Because we are accessing memory 2 times. 1 time for instruction fetch, 1 time for actually access to memory. And that's actually the slowest time. And let's consider that, how we can do that using pipelining. So in load award, we have instruction fetch. We can do instruction fetch at the same time program counter, adding program counter to go to the next instruction. For instruction decode, we can decode instruction fields, get register sources and destination and immediate values out, and then read base registers and generate immediate values as well at the same time. This part that I'm mentioning is the part that we need to put big registers between. So we can see in this picture, I'm going to show you how. However, next class, we're going to explain that more. Execution, ILU going to get involved. Also creating the address. If we have, we have load, of course. Because we have load, we need to add immediate with the register source to find a new address. It's like an offset access to memory. And then we need to access to memory based on this address that we created and read data from data memory. And at the end, we do write back. We write back the result to register file. So how we can do that in a pipeline, in this picture, you can see that we just need to use a couple of big registers that we call them pipeline registers. They are very huge. You, instead of having like big clock, you can break that to a small part. When you do, for example, fetch, reading and updating program counter in this clock, and then this, and then this, and then this, and then save the result back. Like for example, we also have controller here. I didn't show that. We also have controller here. And controller also gonna create control signals, and we're gonna save those control signals here because the next instruction that can get fetch and create the new is gonna overwrite on those. So we need to save them. So that's the reason. Anybody can say why we have this register at the end? Maybe we say, okay, we're just going to write that here back. Why we need another register here? Actually, we can. We can take this out, but based on those examples, access to memory need loss of time, 250 picosecond. If you take this out, you need to add this with register file reading as well, and also another multiplexer between. So you are kind of increasing the time. So it's better to make that shorter. That's the maximum time. Access to this memory is a maximum time that coming. I said the maximum time is clock. So the maximum time is access to memory that considered as a clock, and we consider all of them equal to that. Even though one of them is, some of them are smaller, still we consider the maximum time, and the maximum time is always memory. So that's why we put this to not increase that clock. Okay, we're going to see examples to understand that more. Any question about this? Okay, so let's have more ideas, like emphasize more. First of all, so we already explained that we need to start next instruction before finishing the current instruction. So instructions kind of overlapping, okay? And it increased the utility. We already explained about that. It improved throughput. Yeah, something very, the throughput is the number of instructions in overall, in a time, in a certain time is a throughput. We are increasing this throughput because we are actually have more instruction completed per unit time. The throughput is that the number of instruction that can get completed in a unit of time is called throughput. We are increasing throughput. What about we also talked about, okay, I'm going to talk about that in very short. What about latency? Yeah, this is what I wanted to mention. What is latency? You already talked about latency as well. We said latency is the time that one instruction from the start to finish. The time that we need to finish one instruction from fetching to write back, that's the latency. I'm going to ask you guys, do you think pipelining can help latency or not? It's going to make the latency better? It's going to make it worse? Should be the same? But who says that is going to make it worse? Who said it's going to make it better? I mean, make latency better. You say it's going to make it better? Who's going to say it's going to make it equal? Latency is not changing. Okay, so it means the time that instruction come and the time that finishing is always equal. If you use pipeline or not, this time is equal. What I'm saying is even worse. If you use pipeline, latency even get worse because the time that instruction coming and going is going to get slower. Why? Because we need to put some slot and some wasting time between some instructions, between some spot that sometimes without pipeline you can do them faster. Like for example, we can see that in the next page. So clock cycle is limited by a slowest stage. This is very important. Actually, that's the reason that sometimes latency is actually get worse. Because we are choosing clock cycle, we are choosing these small clock cycles based on a slowest stage. Based on a slowest stage. And a slowest stage is most of the time memory. And some stages are idle, depending on instruction. Like, for example, in a store, writing back stage is idle, but still we are considering that time. Even though, for example, latency for a store without pipeline needs, for example, this 4, here we consider 5 clock for that. Because the latency is from start to end. Latency is this time, not this time. Throughput need these times plus this. Like for example, what is the throughput for here? For 3 instructions, 1, 2, 3, 4, 5, 6, 7. That's the throughput. And what is latency? Latency of all are equal. 1, 2, 3, 4, 5. 5, 5. So you can see why latency gets worse. Because latency, if we run a store individually, is 4. But here, because we use pipeline, we put another extra that we don't need it. But because we want to be regularity, remember? We need to add that extra stage. We're going to see that in this example. So this is a computer that memory need 200, ILU need 200, register file need 100. It didn't give extra information, so it means, for example, accessing registers, register file, they are writing or reading are all similar. So imagine we are doing single cycle. In single cycle, we have 3 load instruction. In single cycle, we need instruction fetch, 200, register read, 100, ILU, 200, data memory, 200, and register write, 100. So 800 each. So 3 of them gonna be how much? 3 times 800. So the total delay for each instruction is 800 picoseconds. But what about pipeline? Imagine we use 5-stage pipeline. First, we need to find clock. Clock is a maximum. The slowest stage or the maximum picosecond is 200. So we choose clock 200, 200, 200. And first, we fetch the first one 200. The second one, we access register. Even though it needs 100, we consider 200 because we want to make them regular. And this is for these 3 instructions. As you can see, if you add them up, the overall gonna be for 4 instructions. If you compute a speed up, is actually 800 over 200. That is 4 times. So a speed up is 4 times. It's supposed to be 5, but it's 4. Why? Because of these issues that we have, this wasting time that we have. And that's the reason that even though throughput get better, latency get worse. Like as you can see here, latency get worse because we are just wasting time in this. Without pipelining, we do that 800, but here we do that 900. Actually, 1,000, sorry, because we have another one here too. I forgot that one too. Any question? Okay, that was information that I wanted to share with you about pipelining. Next class, we're going to talk about hazards. So if you have any question about your that project or discussion, just send me email. Yes.
I did have one question about the project. Are the registers going to be 32-bit or 64-bit?
Up to you.
Okay.
Yeah, up to you. You can do whatever you want.
We just need to be able to complete those.
Yeah, but make it regular, maybe 32.
Okay.
Yeah. But I had one example, 32, I think. Make it similar to that. Don't make it complex.
I saw the 32 on the immediate generator output to 64-bit, so that's why I was confused between the two.
Make it 32. You are talking about the memory, yes? The size of the memory. Huh?
The registers themselves.
Or registers as well. You can consider both 32 or whatever. As far as not makes it more complex, up to you, whatever you want. But I think 32 is make both 32.
That's what I have currently. I mean, it makes sense because then I can go full word.
Yes. You have question? A code?
Yeah.
1201. Yes.
I have one question
About?
project.
Yes.
It says to make memory of word addressable. Does it have to be, or can it still be like byte addressable?
Did I mention word addressable?
Did. I don't know if that's.
That's up to you.
Okay.
Yes, up to you. Yeah.
Thank you.
But mention that if you are using Word, mention that this is
Sounds good. Thank you.
You're welcome.